Hi class, this is topic B6, momentum and impulse. So the learning goals for this lesson or for this video are to recognize momentum as a vector quantity and solve related problems, to understand that impulse is the change in momentum and solve problems using equations or graphs, and describe the applications of impulse in real-world situations, such as the importance of follow-through in sports. So linear momentum is the product of an object's mass times the object's velocity. We use the symbol P, and it is a vector quantity with units of kilograms, meters per second. We don't want to forget that momentum is a vector quantity, and that means when we're solving for momentum as the final answer, you need to include direction. Note that the direction of momentum is the same as the direction of velocity. So the more momentum an object has, the more difficult it is to bring to a stop, which would be the case for a massive object, even at low speeds, like an elephant, or a very fast-moving object, like a bullet. And so it makes sense that our new equation reveals that momentum is proportional to mass and proportional to speed. Also, as an object picks up speed, like a soccer ball rolling down a hill, we might say the object is gaining momentum. So let's try an example. Calculate the momentum of this elephant and the momentum of this flying piece of sushi. So out of the givens, we have the mass of the elephant, 2,300 kilograms, and it's traveling at 25 kilometers per hour. Right away, you should have be in the habit of changing your kilometers per hour into SI units. So we're going to show our unit analysis and not round that number early. Then we're trying to calculate the momentum, and we have an equation that connects our givens with momentum. So we just substitute in 2,300 kilograms times our calculated speed in SI units to give us 16,000 kilogram meters per second to the right, or forwards, I guess. Forward is the way that the direction is indicated on the velocity, so we're going to follow that same convention. 2 sig figs. Part B, calculate the momentum of a 0.05 kilogram piece of sushi traveling at 1.4 meters per second backwards. So we have these givens. Make sure we convert to SI units. And we have our equation that's momentum is already isolated, so we substitute our numbers and we get 0.070 kilograms meters per second backwards. Don't forget direction. Momentum is a vector quantity. So now let's talk about changes in momentum. Since momentum and speed of an object, since momentum is proportional to the speed of an object, the object will undergo a change in its momentum anytime the velocity changes. So if we can have an object gain momentum, that's their gaining speed. What might cause this? Change in an object's speed or a change in an object's direction, or both. All of those are results of acceleration, which is caused by a non-zero net force. Change in momentum is referred to as impulse, and we use the symbol J. J is the change in momentum. If we substitute mass times change in velocity and make a substitution for delta V, and then multiply by delta T and divide by delta T, so since we're essentially multiplying by 1, that doesn't change the value of the right side of this equation. We've done some simplifying to reveal a new form of Newton's second law, where impulse is equal to total force times change in time. And this is the time that that force is applied. And when an object gains momentum, it increases speed. And now that we can see from this equation, our units of impulse are newtons times Newton seconds. Newton seconds. Oh, and also that impulse is a vector quantity that is the same direction as that total force. So these different options that we have for our equations, which one we use will depend on what we're given and what we're searching for, what we're trying to solve for. And notice the units of impulse are different than the units of momentum, even though they're equivalent. Even though they're equivalent, when we're asked for impulse, you will be required to report Newton seconds and report momentum as kilograms meters per second. I always say if two things are confusingly similar, let's put them right side by side. Newton meters, we have learned before in a previous lesson, don't accidentally write Newton meters instead of Newton seconds. So Newton meter is equivalent to joules. That was when we had work. Kilograms meters per second squared, that was equivalent to newtons. So when we want momentum units, don't accidentally write that. It's kilogram meters per second. The seconds is not squared here, and this is newtons seconds. Let's try an example where we're finding the impulse. So writing out our givens, we have mass, 0.045 kilograms. We convert to SI units. The final speed is 40 meters per second. We're hitting a golf ball. So those two numbers, that's all that's given. It's not quite enough to solve the problem. Find the impulse. If the ball starts from rest, the ball is resting at rest on the tee, so VI is 0. So our impulse, which is the change in momentum, it's just our final momentum minus our initial momentum. Since initial velocity is 0, it's just mass times our final velocity. So how much momentum is gained? It's the impulse. It's 1.8 Newton seconds forwards. We say forwards because that's what was implied by the velocity there. Okay, let's try another example, a longer example. A 2-kilogram baseball is initially moving with a velocity of 22 meters per second south when it is hit with the bat. If the final velocity of the baseball is 35 meters per second north, notice the different direction, what impulse does the ball experience? And if the collision between the bat and the ball is 0.08 seconds, what force does the bat experience? So we're drawing a little diagram. We start out traveling south. Then we end up traveling north. Just like we've done with kinematic equations, I don't recommend writing out the directions in the given section. I recommend just drawing your diagram and deciding a positive direction. In this case, I said arbitrarily that north will be positive. So my north value is positive, my south value is negative. So my change in momentum or my impulse is equal to m times delta v. I make the substitution, being mindful that I'm in SI units and that I have the correct sign. So 35 meters per second, subtract negative 22 meters per second, it becomes addition, and we get 114 kilograms meters per second. And we know that's equivalent to Newton seconds. And since we're asked for impulse, we are going to make that substitution. And the direction. So since we assigned positive to be north and we got a positive number, we're going to say that the answer is north. So our momentum gained is north. Okay, so this equation is called the impulse momentum change theorem, just stating that impulse is equal to the change in momentum. And we can see from the equation that applying a large force with a short amount of time could produce the same momentum as applying a smaller force for a longer time. We could use this equation to explain the importance of follow through in golf, tennis, badminton. The force is based on our strength. So if the force is set, if we add the follow through, this increases the collision time, and we increase the amount of time that the force is being applied. So we're increasing, this is set, and we've increased time. That means we're going to get more gain in momentum, which is more speed. So we'll increase the speed of the ball as it flies away. And another sports, I guess, application is cushioned catcher mitts in baseball. So a ball has a certain speed that it starts with, and it must come to a stop. So the delta V is set in this example, and in this like real world application. So the delta V and the mass are set so that impulse is set. So if impulse is set, what can we play with? If we increase the time by having a cushioned mitt, then we can reduce the force that we experience, and it will be less painful when you catch the ball. And the force here is either a constant force or more realistically, an average force. So in real world scenarios, the force will be changing over time. When contact begins, the force is low, and then we have the point of maximum compression, and then there is the contact ending, force tapers off. So when force changes over time, what force do we substitute in to the J equals net force times time equation? Well, we could have an average force, and that would work, but otherwise we could do it using the area under the force time graph. So we might have a very short contact time, or in a very steep curve, or we could have a long contact curve. So this is like the catcher's mitt where it's widened, so the area under would be greater, the impulse would be the maximum for, if the impulse or the area is constant in the catcher's mitt example, whether we use the mitt or not, the impulse is set by the initial and final speed. We widen out this curve. So area under the force time graph is impulse. So you might just ask yourself how these graphs look different. If impulse is set, and you increase or decrease time, versus if force is set and you increase or decrease time. So what would happen, or what would be different? So I encourage you to read that section in the book to get a few more sports examples. And I'm also going to link the physics classroom interactive page for you to explore those applications. So if the average force is given, what is the meaning of that? So average force times delta T to get impulse, it's the force that would give an equal area. This rectangle would be the equal area to under this bell for that same time interval. So the average force, if we did F times T in this shaded green area, that would be the same as doing the area underneath this bell. So our last example, we have a 0.43 kilogram ball initially at rest is kicked and experience a force as shown in the diagram. The force time graph is given. So the collision loss or the interaction, the force is applied for 1.2 seconds and the maximum force is 25 newtons. The impulse imparted by to the ball, so how much momentum is gained by the ball. If it's initially at rest, the initial momentum is 0. So final minus initial momentum, or the impulse would just be final minus initial momentum or just final momentum. because initial is 0. So we get that by doing force times time if we know the average force, or if we're told it's a constant force, but we're not told that. We're told the force goes from 0 to 25 and then 25 to 0. Area of a triangle is 1/2 base times height. The base is 1.2 seconds and the height is 25 newtons. Multiply that by 1/2 and we get 15 newton seconds forwards. The final velocity of the ball, now that we know momentum equals m times v, so v is p over m to solve for the velocity of the ball. And the average force exerted, well, if we know delta p is also equal to F times delta t, we can do momentum divided by t to get that average force. And let's go to our final answers. So you can pause this video and calculate the numbers. And see if you get so for the final velocity of the ball, you should get 35 meters per second, and the average force exerted, 15 divided by 1.2 seconds, would be 12.5 newtons or 13 newtons. Okay. So our practice questions, so it's really important that you practice. This lesson is sort of an intro to those concepts, and it leads into much more challenging conservation of momentum questions. Much more challenging conservation of momentum questions are coming up, so it's important that you practice. So these are the practice questions that I've selected. And remember to check your answers with the textbook solution PDF located on the Google Drive. Make sure on the Google Classroom assignment, you filled out this exit ticket that relates to this video, as well as submitting these actual questions so that I can give you some feedback and that I know you're on track. Have a great day.